We will discuss our recent results regarding grant function spaces, and we will discuss, we are focused on the general case, especially on general grant Banach function spaces. These spaces are defined on quasi-metric measure spaces with doubling measure, but results are new even for Euclidean, for domains in Rn with Euclidean measure. So, the results regarding general grant Banach function spaces can be used for special spaces, for example, to get appropriate results for weighted grant Lebesgue spaces with Magenhaupt weights, weighted Lorentz spaces, again with Magenhaupt weights, variable exponent Lebesgue spaces. Okay, and so we are focused on extrapolation theorem. Extrapolation theorem. I will, of course, mention what is Rubio de Francia's extrapolation about the history. By this triple x d mu, we denote a quasi-measure, quasi-metric measure space with a doubling measure mu. Doubling means that this condition is satisfied, where the constant d mu is independent of x and r. B, x, r here are balls. And we will assume that measure is finite, so mu of x is finite. Okay, so suppose that w is a weight function on x. So as usual, measure it is locally integrable function, but since we deal with a finite measure, here is integrable w, and theta is a positive constant. So what is a weighted Ibanez-Bordone space or weighted Grant Lebesgue space with measure w? This is the set of all measurable functions f for which this norm is finite. So what we have here? We have a Lebesgue, weighted Lebesgue norm here. It is multiplied by epsilon theta over p minus epsilon. So this norm, it is p minus epsilon. It is multiplied by epsilon theta over p minus epsilon, and supremum it is taken with respect to epsilon between 0 and p minus 1. So when w it is 1, this is, and x it is, theta is 1 and x is omega. This space was introduced by Ibanez and Bordone in 92 when they studied the problem of integrability of Jacobian. Later, this space was extended, generalized by Greco, Ibanez, and Bordone, and they took their theta greater than 1, and they used this space when they studied solvability of certain nonlinear partial differential equations. Here, if we take formally theta is 0, then we get a classical weighted Lebesgue space. These spaces are interesting because they are not separable. For example, the closure of let's take over domain. This space defined over domain. For example, C0 infinity, closure of C0 infinity, it does not coincide with this space, is not separable, is not reflexive. There exists investigated its associate space, which is called small Lebesgue space, but the space is not reflexive. It is larger than classical Lebesgue space, but it is contained in Lebesgue space with power with exponent p minus epsilon. The following good properties it has this space. For example, the Hardy-Littlewood maximal operator, well-known Hardy-Littlewood maximal operator, it is bounded in this space with weight W, even only if W belongs to the Magenhaupt class, well-known Magenhaupt class. We will have below, I will remind you the definition of this class. So this was a pioneering result by Fiorenza, Gupta, Jain in 2008, when they proved this theorem. Later, jointly, the speaker jointly with Vakhtang-Koklashvili, we proved that the Hilbert transform, it is bounded in this space, even only if the weight belongs to, again, to Magenhaupt class, AP class. And more later, by the speaker, it was established also criteria for the one-weighted Sobolev inequality in these spaces. Okay, so about the results, progress, and the properties of these spaces can be found, for example, in the second volume of this monograph, jointly with Vakhtang Koklashvili, Humberto Rafeiro, Stefan Samko. It was, this is volume 2, published in Birkhauser in 2016. Now let's pass to general case. I will remind you what are Banach function spaces. So, assuming that we have the set of all mu measurable functions, so the Banach function space, it is Banach space defined on this set, having the following properties. For example, in the book Bennett Sharpley, you can find the definition that the norm here is 0, even only if f is 0, mu almost everywhere. This is the lattice property. If g modulus less than or equal than f almost everywhere, then we have the same for the norms. Then we have the Fato property. If fj, it is increasing sequence of non-negative functions converging to f, then we have that the norms are also converged to the norm of E. This property, for property that if the measure of f is finite, then its characteristic function belongs to this set. And the fifth property, that if again it has finite measures, then integral over f on this set, it is less than or equal to the constant C f multiplied the norm of f. Okay, and here in Banach function space, it is defined associate space denoted by E prime, which is the collection of all measurable functions for which this supremum is finite. So this is the standard definition of associate space. Okay, so here are listed well-known examples of Banach function spaces. So in fact, since I don't have much time to discuss, we will focus in fact on two spaces. First two spaces, Lebesgue space, weighted Lebesgue spaces, and weighted Lorentz spaces, because to prepare the stuff for variable exponent Lebesgue spaces, I need more time. That's why I removed this part. So for a Banach space E, the P convexification is defined in the standard way. So E to P, this is the collection of those F's for which modulus of F to the power P belongs to E. EP can be equipped by the quasi-norm, by this identity, and when P it is between 1 and infinity, then this is again, it is a Banach space as well. Okay, so on the basis of Banach function spaces, recently it was 2021 in the paper of the speaker with Vakhtang Koklashvili and Mechislav Mastillo, and independently Monica Singh, we introduced a general type of grand Banach function space. So we denote this by this symbol, which is the collection of such measurable functions f for which this is in fact the norm, this is finite, this supremum it is finite. So we took here the function phi, measurable function phi defined on interval 0 p minus 1, which is non-decreasing and having this property that the limit it is 0. So we raised to appropriate power and multiplied by this norm. And if the supremum is finite, we say that f belongs to this grand space. Okay, we denote such phi functions phi, which I just mentioned, by capital phi p. So if phi of epsilon it is epsilon to the power theta, then we denote this space just by e pi theta. Okay. For this general Banach grand Banach function space, the following properties are true: that it is again a Banach function space. This space for phi belongs to EP. So this is this space contains. So here is contains E, the space E itself. For all epsilon, we have such a sorry. This is true. This is true. The second it is true. Here is just that E to P it is contained in EP phi, and on the other hand, it is included in EP minus epsilon. And for example, if we take the closure of L infinity in this space, and if we denote the latter space by this symbol, then it is described as follows. This is a collection of those functions f for which here is misprint. Here should be the norm of f, in this. So the norm should be 0. The norm. I apologize for this. I mean the following, that the limit phi 1 minus epsilon f e p minus epsilon. Epsilon goes 0, should be 0. So, and yeah, and its associated space for this grand Banach function space, it is called a small Banach function space, and it was described by Monegasing in that paper. By the way, first, for the classical grand Lebesgue space, small Lebesgue spaces were introduced by Fiorenza in the beginning of this century. This is the well-known definition of Magenhaupt classes. So we say that f belongs to AP, P it is strictly greater than 1, if this supremum here is finite. Okay, and here supremum it is taken over all balls in X. And A1 class, we say that a weight function belongs to A1 class if its hardly little maximal function, 0.5 is less than or equal to C times W of X, where C does not depend on X, mu almost everywhere. So by M, we denote the hardly little maximal function on X. And here, as well as here, by this symbol, we denote this supremum. This is called, as usual, Magenhaupt characteristic of a weight. So this supremum just, and in the case of A1, we call characteristic A1 characteristic of weight function W, just best possible constant in this inequality. There exists a class, A infinity class, Magenhaupt class, which is the union of all Magenhaupt classes AP, where P is greater equal than 1. So what is the original Rubio de Francias extrapolation theorem? It was treated a linear operator and says the following, that if for some fixed P0 and if for all W weights AP0, a linear operator, it is bounded in LP0 W, then for all P greater than 1 and for all W, which belongs to appropriate AP class, T it is bounded NPW. So for this property from P0, we have the same property for all P. For example, if it is enough to prove the boundedness of the linear operator for A0, for A2, as usual done for many operators, for example, for Calderon-Zygmunt operators, and then from this property, if we begin from P is equal to 2, we can conclude the same property for all P, which is greater than 1. Okay, so extrapolation was studied. There are many papers devoted to the extrapolation property. For example, this monograph, Gruzuribe Martel Perez in 2011, there are given many results in this direction. In particular, in variable exponent Lebesgue spaces, they established this property. So by these authors, so they proved that if we have the boundedness of operator in LP0 W, for W belongs to AP0, then this operator, it is bounded in variable exponent Lebesgue space. So they proved such a statement. So from constant weighted Lebesgue space to variable exponent Lebesgue space. So in grand variable exponent Lebesgue spaces, it was established by the speaker with Vachtan Koklashvili. In weighted grand Lebesgue and Lorentz spaces, we studied again with Vachtan Koklashvili. And in general cases, there are recent papers, for example, by Ho, he has several papers by this author, for example, recently last year published in Lorentz spaces, did fundamental investigation of extrapolation in general Banach spaces. Okay, and now, what about our results in general Banach function spaces? So, suppose that calligraphic E is some family of pairs of functions, or measurable non-negative functions on X. Let's suppose that for a fixed P0, which is greater than or equal than 1, and for all weights W from this space, and for all this cup, this inequality holds. This inequality holds. Where constant C, it is a structural constant, but this constant here depends on the characteristic of a weight function, and this dependence, it is such that this mapping, it is non-decreasing. As usual, for all integral operators, it is true. Then let E be a Banach function space, and suppose that there exists a Q0 such that this is again a Banach function space. Then for every P which is greater than 1, for every phi from that class, there exists a constant C such that again for all cups F and G from that calligraphic E, this inequality holds. This inequality holds, provided that the associated space of this space, it is such that the Hardy-Littlewood maximal operator, it is bounded here. So I forgot to mention what is this class, but And moreover, supremum, such a supremum of norms of a hardly to the maximal operator is finite, where sigma it is small positive number. Okay, so in fact, I will stop for a moment here. So as usual, this property, what is given here for example, this property that the hardly to maximal operator is bound. It is true for, we will see later, for weighted Lebesgue spaces. It can be done because of the openness property of the Markenhaupt weight. For variable exponent spaces under the log-holder continuity condition on exponent, for Lorentz spaces, okay? And now, as I mentioned, we can how we can apply this statement. Of course, it can be applied for linear as well as nonlinear operators, because instead of that cup fg from epsilon, this cup, so of course we can take the cup f t of f, where t is operator. So, and that's why it is useful to establish the boundedness of integral operators of harmonic analysis in those spaces which I mentioned. Why? Because operators of harmonic analysis, they are bounded in Lebesgue space under the Markenhaupt condition. Maximal functions, Calderon-Zygmunt singular integrals, commutators of singular integrals, okay, and there are also some other estimates, okay, and this is, for example, the case when we have the case of Grand Lebesgue space, okay. I will formulate for Grand Lebesgue space, and I see that I don't have time to go to Lorentz spaces. I will stop here. So suppose that we have this triple x d mu, and p0 it is fixed. Epsilon, this E calligraphic E, it is the pair of all non-negative functions, measurable functions fg, and suppose that for all for this fixed p0, for all this cup, and for all w, this inequality holds, where again n it is the constant depending on the characteristics, such that this mapping is non-decreasing. Then for all p, for all positive theta, for all w which belongs to AP, and for all cups which belong to the same class, we have appropriate one-weight inequality in Grand Lebesgue space, where of course C bar it is the constant which is independent on F and G, couple F and G. As I mentioned, we can take, for example, a sublinear operator instead of G, and formulate the extrapolation result for sublinear operators, okay, in these spaces. As an application, we can consider, for example, Calderon-Zygmunt operators. So here is given the definition of the Calderon-Zygmunt kernel defined on a space of homogeneous type, okay, and then we can apply that result to establish, for example, the boundedness of the Calderon-Zygmunt operator, not only in the weighted Grand Lebesgue space, but also weighted Lorentz space, Grand Lorentz space, Grand variable exponent Lebesgue space, okay, as well as for commutators of Calderon-Zygmunt operators, okay, we can do the same, since commutators of Calderon-Zygmunt operator, it is bounded in LP W space when W belongs to Markenhaupt condition. So I see that I don't have much time. That's why maybe I will stop here. Okay. Thank you for your attention.